Yeah, thanks everyone for coming. So today I'm going to be talking about kind of transformer networks and kind of how they relate to Monty, what kind of similarities there might be between them, and kind of key differences. And yeah, obviously ask any questions as we're going along, as always. And I guess, yeah.
Was the aim of this to see if we can help?
Yeah, so there's a couple aims. So the first aim is kind of identify sort of possible cross-pollination between these. So that's right. So, what can we do to, maybe improve transformer networks while we continue to kind of create the true Monty system, as well as, maybe there's some ideas from transformers that would be useful for Monty. In general, in the discussion, I'm going to focus on kind of the current implementation of Monty as it stands, rather than kind of the thousand brains theory as it kind of generally exists. And the kind of main reason for that is it just makes it easier to talk about kind of concrete details and draw kind of more kind of explicit parallels. And then just kind of in general, we identified at the last By the Bay that we want to kind of improve communication between Monty and Mega team and just kind of general understanding of what we're each working on and get influence from each other. And so, if Monty is kind of a big kind of epic castle on a mountain, Mega is this transformer, then we want this kind of, I don't know, cyberpunk castle on a mountain.
All right, that's a stretch.
And then
did you use stable diffusion to change that picture?
It was a DALL-E 2. And then I think it'll also just be interesting to kind of maybe contextualize some of the recent gains and hype around transformers. If they have kind of just through their design incorporated some concepts from kind of the thousand brains, then maybe that explains why they have been able to achieve certain things, but of course are still limited. And in terms of limitations, obviously there's many, but just the sheer amount of data that these things require, all this, it might be kind of possible to understand a bit better. And kind of on this topic as well is just kind of recent work in this area. So transformers being used as embodied systems is becoming kind of an active area of research. And so I'll be talking about a couple papers in that area. So just kind of a quick preview. So these are kind of like some of the similarities that I'm going to touch upon. It's important to emphasize that similarity does not mean equivalence. I'm not saying that these things are identical, but that these are just kind of some kind of things where you can definitely see relationships between the two. So yeah, the connectivity that exists, this kind of concept of kind of a common representational format, how kind of voting operates and how that relates to self-attention, which will be kind of the thing I spend the most time on, kind of reference frames and how that might relate to positional encodings in transformers, and then embodiment, which as mentioned is now kind of a topic of research with transformers. But obviously there are many differences, and although this list isn't exhaustive, the connectivity can be similar, but it's also different in many ways. Of course, the kind of whether there's explicit object models is a huge one, and how learning is taking place is another really big one. And then, when I talk about embodiment, you'll see some of the approaches that are currently being adopted with transformers are just a bit kind of curious if you compare it to kind of the thousand brains mentality. So before I get into it, so I guess, I'm hoping everyone's kind of fairly familiar with Monty and fairly familiar with transformers, but I will just kind of cover them a bit. Obviously, if either of them are more new to you, then stop me and we can go through in more detail. But yeah, just to kind of emphasize that with the kind of learning modules in Monty at the moment, we're getting in these features with a pose to update the kind of evidence for these explicit kind of graph-like models. And in order to kind of process that, we have kind of a buffer of where we were before, and given kind of our new position, how we move through space, that gives us a displacement that tells us kind of where we're moving each hypothesis along this kind of space. And these hypotheses are based on our kind of memory of these graphs. These hypotheses can also be used to vote with other learning modules. And then we can output essentially a pose of where we, the kind of object and the pose of that object, as well as potentially an action. And then a transformer is, composed of these kind of key blocks, kind of repeated throughout. And really the kind of key thing that makes transformers what they are is this self-attention operation. And so I will go into a bit of detail about kind of how this works, just so everyone's on the same page, but I'll do that later when I talk about voting. But the kind of general thing to kind of be aware of is, these were created in the context of natural language processing. So where you'd have a series of kind of token representations. So for example, words in a sentence, these are kind of processed in parallel by this self-attention mechanism, which is essentially kind of comparing all of these words and how they relate to one another. That gives you this kind of new output, which will be done for kind of many different sets of weights. And then this kind of feed forward system is just a way of kind of combining that information. And then you essentially just repeat that. But you get this kind of stream where you're kind of just any given token is sort of passing through in this kind of given stream on its own. But then whenever there's a self-attention operation, that's where it's kind of looking at the information around it and combining that information. So this is very different from the kind of the typical fan-in and CNNs and so forth. And then it's also just important to note that with transformers, at the input, you have this positional encoding, which because otherwise the sequence, there's no information in the kind of where these items are relative to one another. They're going to be processed in parallel all at the same time. So you need to kind of give some sort of positional information. And so, for example, in the original paper, this was using some kind of sinusoidal and cosine functions, and was literally added to the vector of the kind of feature representation to kind of capture that.
How would encoding be encoded in a sinusoidal or cosine? I don't understand.
So essentially, it's like you can imagine it's a little like grid cells, to be honest, where you imagine you have a bunch of sine functions of different frequency. And so let's say you're the fourth element of the sentence, then you are going to kind of plug in 4 into these different sinusoidal functions. Those will give different amplitudes depending on their kind of frequency. And it's those values that are kind of form a vector. And that's what's used.
So is that vector actually represent a position in a sequence of words?
Yeah, so it represents an absolute position. Yeah.
So the sinusoidal.
Or you can infer a bit like how from a set of grid cell modules you can infer from these functions where your position is, and
okay.
And the reason they chose that actually was because that works for sequences of arbitrary length.
And it sounds like nearby positions will also have slightly similar encodings. Yeah,
exactly.
I guess it'd be interesting sometime to understand that mechanism more explicitly, because you say there, it's a little bit like grid cells or adding sinusoids, but those sinusoids and grid cells are representing vectors of movement, and you're trying to update a representational location. I just don't know how parallel that is. I don't think we can get into it now, but it'd be interesting.
Yeah. I feel like it's, from my understanding of it, of how it's implemented, at least, I think it's pretty similar. I think the key thing is it's one-dimensional, and this is like a common theme throughout transformers that I don't know if it's because they originated in natural language processing, but
right. So
even when 2D images are processed, they tend to just treat it as a raster and use one-dimensional embeddings rather than a 2D.
I don't want to get off topic here too much, but this might be a very important aspect of the whole idea you're presenting today. Is it's one-dimensional, but there's different, but it's one-dimensional. It's not clear if they're representing. Is it just an ordinal, order like first, second, third, fourth? Or is there sort of temporal aspects to this? I don't think there would be, because they're not processing this in time.
No, it's just a fixed, it's just a position. So think of this as, let's say, 4 different 1D modules, each
Yeah.
with different frequencies,
You know,
and then together you're representing a position in 1D.
yeah,
That's basically it.
yeah. Then,
But they're doing it analog,
where,
they're adding it up.
where do those frequencies come from?
It's just a parameter.
Yeah, it's just a parameter.
Who determined that parameter?
Hyperparameter.
Okay, I don't understand it. It's okay, I don't understand, but you know,
It's the same with grid cells. Like, well, how do you determine the spacing of grid cells?
well,
It's just you
all right, but
learn,
that's just
right?
spacing, but grid cells I can say are representing, you know, a position in space,
The same here.
which is updated. Well, you know,
And
when I think
this
about
will move
sequence,
it.
well, when I think about sequences, that's not, you can say one dimension, but you can have a one dimension order, and you can have a one dimension, a true one dimension, where the words have like some, you know, spatial distance, like notes in a melody. There's some gap in between. They're not just a sequence, right? It's not just an order. It's an order plus time.
Yeah, so it's kind of up to you, I guess. Like, there's no reason you couldn't use this to, like, here it's sentences. So yeah, so it's ordinal in, so I guess it's kind of ordinal out. But I mean, it's a continuous mapping, or like it's a
Yeah.
continuous output. So if you had a continuous input, you could do that.
Yeah, but you could use this for 2D images too. You could have a 2D
Yeah.
sinusoidal thing, which would be would be more like what we think of as grid cells.
Yeah.
But and I guess when I think of grid cells, I think of, you can't remove them from or think of them separately from movement.
Yeah,
mean,
there's
but-
no movement.
I know, so I'm just trying to, where are the
Yeah. I mean, when I get to the embodied stuff, that'll make sense. But yeah, and I'll talk a bit more about like the different flavors of positional encodings. But just to highlight, the most common approach is to literally add the positional encoding, which is interesting because yeah, I think that's very different from the kind of way we would think about it in Monty, because you know then you're really kind of entangling this positional representation with the feature representation, rather than it being explicit and on its own.
Yeah.
And I don't think that's done for any kind of like it is possible to concatenate them instead, but it's just in order to keep computations low, they basically do that. Okay, so a bit of background then done. So then on to kind of the first thing, which is just this architecture kind of connectivity. And so what I'm showing here first is kind of Monty and the kind of general architecture of it. And I'm kind of trying to emphasize in each one of these units the kind of the representations that are being computed and kind of handled, which is why I've kind of broken it up into this kind of pose and ID representation, because it'll just make it a bit clearer, kind of the similarities. But yeah, in you know Monty, you have multiple learning modules, potentially with this kind of hierarchical relationship. I'm not showing all connections here, but as we currently implemented it, you kind of get this the sensory modules coming in, and just kind of one important thing to highlight, as well as the kind of voting, these lateral connections. You have a one-to-one connection going from a lower level to a layer above. At the moment, we don't have any kind of fan-in connections, and it's something we've kind of discussed, but in general, the kind of view at the moment is all of the kind of interactions between kind of across a layer of processing are primarily going to be handled by the voting. And then you have these skip. Oh yeah.
A small detail. I think one thing we do allow is to have multiple lower level modules fan into a high level module if they are within that high level module's receptive field. So if
oh yeah, that's true. Yeah.
the higher module has like a larger receptive field and all the lower ones have like small parts of that receptive field, they can all input features into the higher one, but the higher one can't distinguish their locations from each other because
yeah, so it's kind of I guess if this was kind of broken down into 3 submodules, kind of thanks. But then the kind of the location information is still kind of this one-to-one mapping. And yeah, on that, then there's this kind of almost skip connection where, as well as getting the kind of learning module 1 gets this direct input from a sensory module, learning module 4 gets direct input from a sensor module, not necessarily sensor module 1, but of at kind of the same location in space. And then a transformer, if you kind of ignore that feed forward layer, I was it can still fit into this, but just kind of put that to the side for the moment. You can kind of imagine potentially each token as a column, where these tokens kind of communicate laterally with the self-attention mechanism. And as kind of mentioned, whenever a token's being processed other than self-attention, it's predominantly in this kind of like single feed forward or kind of single track highway, rather than again having like a massive kind of fan-in operation. And yeah, and we have skip connections here as well. And then similarly, kind of the spatial representation is being kind of injected at the start, where the kind of sensory input, quote, may be.
What does pose mean in this case?
Just the positional encoding, I think you're.
Just the positional encoding.
It's not the same as pose we're using in Monty, right?
It could, it's not in the sense that, there's no explicit graph or anything like that. Like these kind of embeddings will, I guess, learn what they learn. I mean, I think there's reasonable evidence that they can learn to represent, positions in space and things like that. But yeah, the only kind of explicit spatial input is here at the start. And as mentioned, even that it's not that explicit because it's normally just kind of added on top of the representation that's for the feature.
You have the lateral connections being self-attention.
Yeah.
It's not a voting type of thing, right? Is it? I mean, isn't the lateral connections more like just deciding so where your attentional heads are at that point in time or something like that? Yeah,
I'll get more into attention later, but basically voting can be considered a special case of self-attention.
Okay.
Assuming everything's kind of set up appropriately.
But they also do like an n squared thing, right? Every token is.
Yeah, but I mean, voting in Monty kind of does the same, but I guess the key difference is there's not learned weights that are doing that. It's just based on the relative displacement. And it's just a question of how much of the tokens or the columns around you want to compare to.
Yeah.
You say those aren't learned? The attention mechanism?
No, they are learned.
Oh.
No, that's the thing.
Monty,
the attention. Monty uses the graphs that are internally learned within each column. Whereas because transformers don't have this explicit graph representation, it's kind of implicit in the weights and how it's kind of transforming between one token and another. Self-attention is definitely a weird one. So I think that'll make more sense with the later visualizations. But
just ask one more question.
Oh yeah, please.
To that point. Cool visualization and comparison. But yeah, when you put object representation into these purple boxes and kind of compare it to a learning module, for example, does that mean in there it can like represent entire objects, like models, like things that cannot be seen in one input? Or is it basically it can recognize the embedding input and then everything it learns are like in the connections to other tokens?
Yeah, checking if I understood. So yeah, so it's I mean, it's literally just like a vector. So it's very like it can represent kind of like I guess whatever a vector could represent. So it can't do kind of a whole graph, but yeah, it could represent kind of an object and I guess some fuzzy features about it. In terms of kind of, if I understand, we're asking like how it would like do object recognition or whatever. Do you mean like is it going to kind of do something that's not bag of features to kind of recognize how parts compose it and things like that?
I guess, yeah. So, I mean, one of the principles of Monty is that each of the columns can learn complete models of objects. While the input to a column never sees the entire object at one time, it can still like recognize it by moving over it over time. Would this kind of transformer architecture be able to do that as well, or it can only recognize the object in conjunction with like through the weight matrices that connected with all the other
no, it has to use these lateral connections. So this is the kind of one of the funky things about transformers, and I think one of the key differences is there's no self-recurrence in each one of these tokens, and so there's no way for it to update its representation other than by these lateral inputs. So it's almost like if you were like, we're not going to have any kind of straw world type recognition, where you're building up models over movement. We're just going to focus on voting, and voting's going to do everything.
It's changing a bit though. So, I mean, the naive transformer stuff, it doesn't maintain any state. So when the next input comes in, it's completely fresh, right? So there's no question, there's no concept of successive inputs. Instead, the idea is you just flatten everything. You just flatten time into a single vector that's in a feed-forward way. But that's not the case with the GPT architectures and these so-called autoregressive transformers. You're sort of successively feeding the input in and actually maintaining the previous state as in
so
keep concatenating stuff.
Right. So
part of ChatGPT you're talking about?
Yeah. So there's I guess self-recurrence in that kind of sense. But it's a weird kind of self-recurrence.
It's weird.
Because it's kind of like if the brain kept expanding, if you assume that these are cortical columns, it's kind of like you deal with sequences in time by just adding cortical columns or recruiting more cortical columns through time to deal with new inputs, rather than saying, okay, each one of these tokens is going to try and represent an object and integrate and maintain a stable representation.
Niels, when you're dealing with long sequences, I don't think that's quite true, because basically you're concatenating what it kind of evaluated previously with the current one and then processing them. And then I think there is a form of recurrence that goes on in that sense.
Do you mean like Transformer XL?
Or like Perceiver?
Okay, yeah, I would need to look at that. But definitely Transformer XL, it was again, that's the key thing, is that they always concatenate, I think, which is very different from.
They didn't, at least when I looked at the Onyx transformer, which basically can take many forms on the computer box. There was the place there where it could add, but there was only a certain amount it could add. In other words, I don't know, maybe double what the normal one was. But then that would be somehow saved on out and then re-represented on the next cycle. So I think it was a finite window that was kind of moving across.
Okay. Yeah, that sounds interesting. I'll definitely I'll check out Perceiver and double check that, because the just to quickly show, like, this is the the Transformer XL kind of passes in these representations here from the previous step. Like, this is the kind of fixed window, but when it calculates self-attention, it sort of concatenates this representation here. But that's it's concatenating. But I'll definitely check out Perceiver. It would be interesting if they do that. And I mean, that's one thing that I'm sure someone has tried something like that, because it's essentially just saying each one of these is an RNN as well.
Well, that's about the only way they can get past the n squared thing, is like Perceiver has like a limited amount of n squared and then tracks across the thing. So they can put in these much larger token sequences and actually derive something that has more scope to it, but just not all at once. It's not self-attention all the time. It's kind of building up. I could be wrong about how much they're retaining in that particular.
The like cross attention.
Well, cross attention usually comes in on the decoder side. So, but yeah, you're right. In a way, it's like. You're right.
I think they use cross attention at the input to basically say like 10K tokens is going to be like cross attention or something like that. And then cool. But
in any case, even if they don't specifically do it, you could see how you could do something like that, right? As long as you have some state built on up that you feed in on the next cycle and become part of the input, if you wish.
Right. But so unless there was any more kind of questions on that, I was just going to then kind of focus on just briefly some of the kind of like differences that immediately kind of jump out. Is firstly, what I was already kind of saying, and which will be broken down into more detail about how these kinds of the lateral operation that's going on is very much dependent on learned transformations, learned weight sets in transformers.
So how would you think about attention heads here? Would that be like considered a model? Like, so if you have 10 attention heads, each column here can have 10 models?
Yeah, I was wondering this. I think the reality, because of how neural networks can operate in such kind of weird spaces. I'm sure they can do many more than 10 models, but I think there would be a relationship between the number of transformer heads and like the number of models that can be learned. Attention heads. But I'm not sure it's nearly clearly like a one-to-one mapping.
I think what happened, at least in some of them, the each head at the various levels kind of learns some aspect, like noun verb syntax or something like that, and then by whatever mechanism, the other heads learn other parts of it. I mean, it's just how it kind of trains. It kind of differentiates during training time, so that there seems to be some functionality on each head. So I'm not sure it's a complete model. It could be more akin to a feature, and that those features are then being, when it goes from the attention head up to the fully connected layer, then they all get kind of scrambled together, and then produces new inputs, and then goes to the next level, and then it tries to discern stuff from that. So the actual structure of what happens in that fully connected layer and how it consolidates information to be fed in as input to the next one is something that I've not seen people talk about a lot. But you can kind of imagine how somehow you're managing to create these streams of capabilities. And at the very end, if you're classifying, there's no real model. It's a collection of features at the very end. So I'm not sure how whether imputing a model to the heads actually is something that they embody, at least in the current incarnation.
Yeah, I think the closest thing to kind of a model is, I'll talk about this when talking about kind of reference frames is a bit like how capsule networks kind of like, they don't have an explicit reference frame about, this is where we're gonna represent this feature relative to this feature. It's more the weight transformations that are learned, kind of learn, okay, I've got a nose, this is where I expect the face. I've got an ear, this is where I expect the face, or whatever. Like it's more like that, which the learned attention heads could be capturing, or I guess like you say, also maybe the feed forward layer. But there's certainly no kind of explicit spatial map that things are being laid down onto.
Yeah. Okay.
And along with that reference frame, there seems to be, maybe I'm missing it, maybe we're going to get to it later, but the whole idea of you're moving your sensors under volitional control of the brain through space is a huge part of this, right? We're not just something not being passed to us. We are actively exploring space and moving in different directions and processing motion, processing movement, keeping track of which requires reference frames to do that. So it's more than just no reference frames. I think it seems like we're missing this whole sensory motor sort of aspect here.
For sure.
Okay, I just wanted that's a huge part. It comes with reference frames, but
yeah, no, for sure. That is very much missing.
Can these work across modalities too? Can you?
I will get to that. I think.
Okay.
Yeah, on the next slide.
Okay.
But yeah, anyways, no top-down influence, no explicit reference frame, no self-reference. These are just some of the differences, but just highlighting at the architectural level, the kind of the connection level. Okay, so yeah, common feature representations. To answer your question in a couple words, yes, they do. So yeah, of course, common feature representations across modalities. This is important for enabling multimodal models. And in the kind of recent work that's kind of trying to move beyond just language into these kind of multimodal, large multimodal models, LMMs, they do exactly this. So, and the basic idea is pretty straightforward. You just take whatever it is you're trying to kind of represent, that could be a pixel patch, that could be a word token, whatever, and you just do some kind of learned projection of that representation into a fixed size vector embedding. And so as long as those kind of vector embeddings are of, they're all 64 dimensions, say, then you can essentially treat them all the same in your transformer and assume that it's going to kind of learn to deal with the fact that one of them is an embedding of a pixel patch and one of them is an embedding of a English word. And this is just kind of an example showing that in practice. From so PAMI is an embodied multimodal language model from Google that came out pretty recently. This was actually one of the main papers that the DLCT presentation was a couple of weeks ago about kind of scaling robotics using large language models. And yeah, basically they take the kind of query, they turn it into these tokens, they take the image, they turn it into these tokens, and then all of that can be passed into this model and used together. But yeah, you'll see how the kind of the embodied part of it is a bit odd, but I'll come back to that. I just wanted to kind of start with those two kind of comparisons, just to kind of ground the rest of the discussion. And then
it seems like a fairly limited way of doing multimodal integration, but I can't say that for certain because I have to study it more. But the way I think about it in the brain is much more flexible than this. But maybe I just don't understand this yet. All right,
I mean, is it that different from?
There's a lot of things here. There's a lot of things here. I think we'd be careful saying, "Oh, look, it does this too." Oh, look, it has object, it has poses. But when you get to the details, they're really quite different in some ways. And so we have to be careful not to just be careful with our language.
But is that different from taking like a sound wave and a few kind of rod cone responses or whatever and encoding that as an SDR?
Yeah, but we don't do that. We never do that. So we only.
Well, I mean, okay.
That would be a terrible way of doing it. The way the brain merges is purely through voting, and they're trying to correlate objects with objects, and it's not a one-to-one correlation. A sound doesn't have to be correlated with a single object, and a single object doesn't correlate with a single sound, and it's a much more dynamic and sort of.
You mean with the spatial pooler, or?
No, we have never done this. I'm just saying how we've described it and I've written about it. This is all done through voting. There's nothing done in the spatial pooler. There's no common. It's just voting. It's like one set of auditory models or a set of tactile models can inform a set of visual models, but it's not one-to-one, and it's not always appropriate. I'll just leave it at that. Is that I look at this and say, oh, this is cool, but to me, it's not the same as I envision multimodal integration in frames. I just want to point that out. That at some level, you can say, oh yeah, there's objects in these modules and there's poses, but they're really the same, right?
Yeah.
We can use the same words for them.
Yeah. So I guess we can be agnostic how like this whole embedding operation. I guess we're not certain exactly what we would do, but I guess the main thing then is once these are input, then throughout this stream, at each level of processing, you started with a visual feature here, you started with the language feature here, whatever. You're going to continue going up those paths, and they're going to continue interacting laterally. So I'm just highlighting that because that is
like
similar to
that these things are one and the same. And that's not the way it is in the brain. They're not one and the same. There are different models in different modalities which can, at different times, help each other. But they're not like, we're not trying to figure out what's in this picture and correspond the language with the picture. That's not what's going on in the brain.
Yeah. No,
and that sounds what they're doing here. They're saying, hey, can we use these two modalities to and combine them in a single representation? I don't think that's happening in the brain. So, and there's a real advantage of not doing it, but this solves a certain set of problems. If you want to have describe images, and if you want to take words and make images, they probably do a good job at that. Okay, I'm just throwing it up. We just shouldn't accept these words as meaning the same thing.
Yeah. No, thanks. Okay, yeah. So voting versus self-attention. So I'll just kind of briefly go through voting in Monty and self-attention in Transformers, and then try and get a bit more into the concrete details of how they're potentially similar. So with Monty, let's say have 2 fingers that we're touching this mug. We're going to get 2 different features at poses. And these are going to be processed by different learning modules, which are going to develop kind of different hypotheses for where we might be on that object. And we have this information about the kind of displacement, including the rotation between these 2 sensor modules. And this is key to the kind of voting process, where we essentially take the hypotheses coming out of a particular learning module, and depending on which learning module that information is going to, transform it by the appropriate displacement. And this is going to give us a new set of points for where we would expect to be on that object based on where we are on in this kind of hypothesis space. And that's what all these kind of clouds sort of exploding out are doing, where there's only a small set of points kind of related to where we were before, that with this displacement are going to move to this point on the handle. And that point on the handle, if you kind of look at your nearest neighbor, you're essentially going to add the evidence that's coming in, which may well be negative, that's associated with your neighbor, and you'll get these kind of hotspots forming, essentially where these are consistent with one another. Self-attention in Transformers is basically a way to kind of figure out kind of representations, figure out what other representations are kind of looking for them and kind of related to them, so it can kind of bring that information together and sort of condense it. When I first talk about this, it won't seem to have anything to do with voting, just to be clear. But that's why when I talk about this as a special case, hopefully the parallel will be more obvious. And when you do this self-attention operation, you have 3 important things. You have a query, you have a key, and you have a value. And for every token, and in this case, we're going to say every word in this sentence is going to be represented by a token embedding. For every token embedding, you will have a key, query, and value. And so if we just focus on this word "it" for now, so this is the word that we're kind of processing with self-attention. So it's going to get it's going to project a query. It's going to kind of basically be asking, okay, what other representations are there around me that might be related, that might be relevant? And in kind of answering that call, every other token is going to produce a key. And so the reason for these arrows is these are vectors. And so you can just think of them as a point somewhere in space. And to kind of determine how much agreement or kind of like how appropriate the 2 are for each other, you literally are just doing the dot product. And then when you do the dot product, so the query dot with this key is going to be a larger value. And then this is just passed through a softmax. And this is what gives the attention mask, the self-attention layer. And so here, the value, this kind of probability associated to the animals, say, is higher. And this kind of fits with the idea that, it is okay. It knows it needs to look for something like a noun or an object or something that it could be referring to. And I guess animal in this sense has learned that it needs to look for words like it that might be referring to it. But what we want to actually.
But the word street, you could make the same argument for the word street. So how does it distinguish between those?
Yeah, this is a toy example.
But just in general, like, all right, that's the trick, right? Is it referring to street or is it referring to animal?
So, well, I guess another thing is this voting operation. It's not just based on, it's based on this embedding, and this embedding is both based on the kind of feature, whatever that is, the object kind of type representation, as well as its position encoding. And so maybe it has learned that, immediately before it, so early before it, it's not going to be finding anything. Like it follows usually later in the sequence relative to the word that it's referring
Well,
to.
that's funny because, I could make the say, I could say the animal didn't cross the street because it was too wide. And in that case, it would refer to the street. So it can't be that simple.
Yeah.
It's impressive, it does it. I just don't understand how it does it. So
Yeah.
I'm not accepting a simple explanation because it leaves me still wondering how it does it.
Yeah. Yeah. What were you gonna say, Vivian?
Yeah, basically the same thing. If you substitute the last word for too wide or too dangerous, it kind of just depends on the last word, what it refers to.
Yeah. No, it's a good point, and that's why this kind of I guess one-to-one comparison is a bit odd that it's doing and how it integrates this. But I mean, it may be a hierarchy thing. I think this is literally extracted from an actual network. I don't think someone made these values up. So I don't know if it here, they've said that the embedding is for the word it, but maybe actually the embedding is for the word it after it's been processed by 5 layers.
Yeah,
And
I
by
was
that
gonna say
point,
that
it's understood. Yeah.
you can look at the evolution from layers. I have that same library, and to look at from layer 1 to 12, it changes a lot. So probably on the first layer, it was referring to street, but then at the second one, it already encompasses the tire as well. So that information is helping decide whether it refers to rain or it refers to street. And you're showing the one at layer 5, so it already
Right.
went to like 5 layers, 2%. But you can clearly see the evolution between layers.
Okay, that helps a bit.
So yeah, so what are we going to do with this?
Clear,
Oh yeah.
I want to make sure I just clear the token
Yeah.
for the word it. There's
Yeah.
nothing else besides it's just a token, right? There's no meaning to that thing other than its associations with other words. Is that correct? I mean, when I say the word street, I have all kinds of associations with the word street. I can, and I can visualize it. I can think about particular streets. I can imagine touching it or crawling across it, whatever. I get, I have a lot of. It's not just a word. It's not just a token. Yeah. And so I've always had the impression that in these large language models, the tokens are in some sense meaningless. The only meaning comes from what they're associated with other tokens. So it's a tokens referring to tokens, but there's no grounding what these tokens mean.
I think there's a learned representation for each word. So street and road might have very similar.
Right, but there's still, it's just all between tokens. There is nothing else besides it's just all correspondence with other tokens. All the definition of one token is how it relates to other tokens. Yeah. And nothing else besides that.
Yeah.
Okay. So
but that's true for every aspect of this. It's
I know. Well, I just
completely on these huge.
But not in the multimodal one. So the new
Not in
one, you
not in
have an association of street, connected image of street,
Right.
But even those are just tokens, right? They're not. I mean, I can make the same argument about the tokens in the image processing.
It would be associating. You would see what sort of images are associated with what sort of words in a stream corpus.
Yeah. Okay.
I mean, yeah. Would the brain have something similar, just with neural activity at a certain?
Well, I think I think the brain. I think language comes after it, right? It doesn't start with language. And we start with a model of the world, and dogs have it, cats have it, and birds have it, and we have it. And then some animals like us have the ability to express that model through tokens like, but it goes in that direction. It goes from a model of the world to a communication token. We start with the communication tokens and there's no model of the world other than the relationship of the communication tokens to other communication tokens. And there's no tie to specific movements or specific behaviors or anything like that. It's just tokens to tokens. That's how it works really well, but that's to make sure I understood it correctly.
Yeah, no, I think that is fair to say, and yeah, exactly. I mean, there's no explicit models. There's no kind of sensory motor really understanding of them.
Well, what if
but yeah,
what if you actually learn a model in a sensory model environment and then you associate it with language?
But that's what we do.
Right, but you could do that here too.
Well, if you had that sensory motor model, yes, but there is no sensory motor model here.
Well, some others do, yeah. That's
Well,
let's get to
yeah.
Let's get to
W-
that.
it-
There's no reference frames, and so it's very hard to understand sensory motor models without reference frames. So I need to understand that better.
Okay, but just yeah. But,
I don't.
oh yeah. Yeah. Sorry. Go ahead, Vivian.
Just might be more of a side question, but is it predetermined where a token starts and where it ends, or can it also learn that on its own? Like, for example, tired
Yeah, I
split
saw
into
that.
2 tokens. Is
Yeah.
that
So
learned, or-
that's yeah. So there's when you are starting with like sentences, like natural language sentences, you have 2 steps. You have tokenization and then the token embeddings. The token embeddings is what transforms it into like a vector of like a fixed length or whatever. Tokenization is how you decide to basically parse sentences into these kind of components. And there's a variety of different ways you could do it. You could do it at a character level, but then your sequences are going to get super long, and so that's really computationally inefficient for transformers. Or you could do it at a word level, but then the kind of vocabulary that you're dealing with becomes enormous. So in practice, most of them do kind of sub-word tokens. So they kind of split up, I think, almost like kind of syllables. And that's what's used, I think, in all the kind of recent GPT models.
Is that true? Like syllables, which is this is showing a couple like that didn't.
Yeah.
And tired. This is verbs that or concatenation.
Yeah. This is definitely, I think, a simplified one.
Do they really work at the level of syllables?
Yeah, normally. I mean, Lucas or someone else can correct me if I'm wrong, but I'm pretty sure that's almost
the
all.
way they do it. So it's actually they start with single characters, but then there is a fixed vocabulary to a read. So I can only have 50,000 tokens. So then they aggregate the least common ones. So you're gonna end up with some tokens which are long, which are like a full word, but they rarely appear. But some ones would just be like 1 or 2 characters.
Interesting.
Like
Interesting. So they say we got 50,000 tokens. Here's a whole bunch of corpus of text. Let's figure out some efficient way of picking out 50,000 tokens that covers all of text.
Exactly. It's like a clustering operation.
Yeah, that's really weird because, well, that's really interesting, but it's also kind of weird. I mean, I can see why that would be good. I can see why it would work, but it's
all a very statistical.
Right. So the tokens themselves may surprise you when you look at them.
Yeah. Some are like very long, and some are just like one.
You got an apostrophe. It's an interesting way of tokenizing language. But once again, it seems like it might move you away from any sort of what we might think about meaning of these tokens. I have some strange little letter sequence that has no meaning on its own, but it's useful in the context of building models like this. Again, it proves that you're really going towards a very statistical approach to this whole problem. You're just taking it that way. Okay, that's really interesting. I didn't know that. That's fascinating.
So I have a question which was brought up earlier. This is at layer 5. So by this time, whatever was the token like animal is now some conglomeration of something else. So the fact that they're pointing backwards to the discrete beginning token, I think, is what's taking Jeff off track on what's actually going on.
No, that's a fair point. Yeah, no, it is a bit misleading.
I don't know. I didn't follow that, Kevin, but I think I understand this.
Well, I think it's important you should understand that this is not a direct mapping. This is an inferential mapping. By layer 5, you won't see the token D or animal or anything like that. You'll see it's gone through 5 layers of transformer that have been processed, and there's a more abstract representation of all this stuff. So you can kind of go backwards and kind of look what the receptive field was, but what you're actually seeing there, what it's saying, it's these things all how they related to it is more abstract. You've already probably parsed out whether it's a noun and a verb and a bunch of other things. So I just want to make sure that the what they're trying to convey here is a concretization of an abstraction, which is much richer.
Yeah, they're putting words on it so we can make sense of it, but it's not like this.
Yeah,
All right,
yeah.
thank you.
It's not literal.
That's helpful.
Great. Yeah, so just the kind of final key element of the self-attention operation then is, so we found out first kind of with the queries and the query and the keys, how kind of how much this token should kind of attend to these other ones and kind of integrate information from them. And in addition to associated with each one of these tokens is this third representation, again, a vector, which is what's called its value. And this is meant to be capturing more, I guess it's kind of semantic meaning directly. And what we're then going to do when updating the token for it, or whatever this is at this point.
I'm sorry, what is it, guy? You said it's semantic meaning?
Yeah, or I mean, yeah, essentially what the kind of the representation that we want to pass onwards. So key and query are about kind of this crosstalk, like how do you figure out who you should be talking to?
Right.
Value is about how are you going to encode your own representation to then pass on to the next level.
All right, and how's that done?
So to get from the kind of current token representation, I'll show that a bit more on this next slide. You just do a matrix multiplication with a learned kind of set of weights to get that value. But the kind of important thing about self-attention is it's going to take all of the values and essentially combine them based on these attention values here. So essentially, the larger the kind of probability from here, the more influence that value is going to have on the updated representation.
But where did the value come from? How's it determined?
The network learns what a good kind of value representation to use is.
It learns that through what mechanism?
Backpropagation.
The backpropagation. Okay.
Yeah, all of this,
Okay.
the key and the query transformations are also learned through backpropagation.
Okay.
It's a parallel operation. Each token comes in, the vector representation comes in, and each of them go through their own separate matrices to produce these values. So that gives you the ability to, at any one stage, produce a query key and value for any incoming token, so to speak.
Yeah.
Okay. Well, as soon as you send me it's learned by backprop, then I stopped thinking of it as in terms of any kind of thing I could think about. It's like
Correct.
Okay.
Correct.
Correct.
It's an
It's
encoding scheme,
misleading.
if you want to wish. It's basically saying, how do these things relate to each other in some kind of statistical sense? But there's a huge amount of context associated with that when you do that, because they kind of pull things apart into query key and value, run through what they call multiple heads, which are kind of representations of the self-attention, then they all get mixed together in another layer and then repeat, for multiple layers. So there's a huge amount of abstraction that you go through in this thing that through the magic of backpropagation, it learns how things are related to each other at multiple levels of representation.
Yeah, but I agree with you that the words query, key, and value are actually more confusing than they're helpful.
If you just said this is a value, this is a vector that was determined by backprop, I'm okay, fine.
Yeah, the only thing that determines like what are the mathematical operations it does to come up with an output.
Yeah.
It's not
Yeah,
really query key.
And it's not, you can't really say it's semantic value. I don't know what you call it. I would just say
Everything's semantic.
yeah, right. It's just something that's determined by the backprop algorithm. So,
Yeah, but I guess, I mean, it will probably tend to like cluster similar representations.
well,
Like
we
it will.
we can go look at it later and try to figure this out.
Sure.
Right.
But-
It's just
and
the
like- and I
structure of
guess
the
you might
operations
have-
will determine something interesting about it.
Right.
Yeah.
Okay.
Yeah, well, and like let's say the animal or whatever, its value is some vector or whatever, and then you have the adjective blue or whatever that's some other vector, and through the self-attention it decides to prioritize those two and combine that. then you can imagine that the new vector direction maybe is kind of this combination of these two concepts, or at least like an interpolation between them. Obviously, it's an open question how useful that actually is, but yeah. That's the basic idea of transformer self-attention. Just to kind of briefly show it again, just in a more kind of vectorized matrix format. We have our embeddings here. These are the kind of vectors coming in. So this, as pointed out, this is layer 5. So they would actually be more abstract at this point than word embeddings. But those are the ones coming in. And we can transform them by these learned weight matrices to get the query vectors, the key vectors, and the value vectors. And you see there's one for each word or each token coming in, rather. And this is just kind of showing the same operation, that basically we're going to do the dot product between the query and the key. You do that for the token itself as well. So it also asks, should I attend to myself, basically? And you do it for basically all of the other tokens that you're going to compare to. Then you do the softmax, you get the probability associated with that. And then the output of all of this is, I said, the kind of scaled sum of all of these values based on their softmax values. And then the last thing I just wanted to say is on this is, as Kevin mentioned, there's multiple heads involved in this. So what does that mean? So as in, you can kind of learn one of these weight operations, but that's going to be kind of reused at every point. So it's going to be, for every token, you're going to use the same kind of operation to do a query, to generate the query vectors and so forth. But you could imagine you'd want to do different types of transformations to kind of, represent different things, different kind of spaces. And so that's what these multiple heads are doing. So they're all going to, each input token is going to get processed by all these different attention heads separately in parallel. And that's going to produce a bunch of these different Zs. And then it's that feed forward layer you saw at the very kind of start. That's essentially just using a kind of multi-layer perceptron to combine those. Okay, so finally onto then some comparisons of this. The kind of proposal is that self-attention can do something like voting as kind of a special case, with obviously some significant caveats. And again, just reminding, the reason I'm talking about all this is not to say that, oh, transformers have already solved Monty or something like that. I'm covering this to try and highlight what are the things that we can maybe make transformers more Monty-like. I mean, that's the main thing. And so, but if we can first understand what similarities there might be.
I'm having trouble parsing this sentence. So it says, are you saying that transformer, the self-intention, is doing something like voting, or that it could if we modified it?
It can, assuming the right weights are learned.
Okay, so it's maybe they're not happening now, but maybe it could be made to do something like voting. Is that? Yeah. Okay.
Yeah, and there's a reasonable chance, though, that it is, because the weights are basically the identity weights. And so hopefully that'll become clear. I'm just showing this again.
But it does sound slightly. It does sound kind of conceptually different, because in Monty, in voting, two models that have learned models of completely different modalities can still vote on like object ID and pose. But here it seems like the entire model across everything would have to be multimodal, like the whole weight matrix and everything.
The entire weight matrix would have to be multimodal.
They're not separate models that vote. They're like one big model that has multimodal stuff. Is that what you're saying?
Yeah.
So as long as the representations have, kind of look similar, there's no reason they can't kind of communicate. Or maybe I'm not understanding what you're saying.
Or I guess in Monty, in voting, we never communicate any model details to each other. So like features are never communicated through voting. Like you don't know if the votes that come in come from a touch model or a vision model. But here it seems like it does explicitly tell you what it is sensing, like the embedding.
Yeah, so I mean, I think even in Monty, you could argue there's a certain degree of that in that, like, I don't know, a 3D model of a mug isn't going to vote with like the abstract concept of a family tree or something like that. Like there's always going to be a degree of, can things vote? But if we assume that the tokens are both like object level representations, like one is like in a multimodal transformer, one's learned mugs through vision, one's learned it through touch or whatever, then those can vote at least at the object level representation.
Yeah, I mean, I mean, definitely to vote, you need to know model of the same object. But I just mean like in Monty, what is communicated through votes seems a bit more limited than what is communicated in self-attention. But yeah, it might just be more of a detail.
Maybe bring that up again when I've gotten to the slide later, because and that's, I guess, maybe why I'm emphasizing special case, because self-attention is doing a lot of things, which I think relates to kind of what you're saying, that it can send a lot of information basically. But yeah, this is just bringing back this kind of columnar view of kind of Monty with these kind of voting. We're going to compute these online. We're going to compute these relative displacements using the sensor modules. Basically, for each graph, we're going to kind of go through and send the transformed poses using this relative displacement, find the nearest neighbors to the receiving points on the object, the receiving poses, and then kind of add this incoming evidence based on your kind of nearest neighbor. And then this is the kind of transformer with this kind of column view. And
this, by the way, this might be a little confusing, but hearing this reminds me there's really two types of voting. We actually haven't really used them out before. Here in this kind, we're saying, okay, well, like multiple fingers touching the mug at the same time. We need to know the relative position. They're in the same modality, which is different. That's not going to occur if I'm going across, like, audition and touch or something like that, where you're not relying on knowing the relative poses of the sensors. You're really doing purely sort of object level voting. So I just want to point out that there was this voting. We have to, if I'm in a particular modality, touch or vision, this relative pose of the sensors is very important, but I don't think it's important across modalities.
Right.
But I think there's actually different. I've always argued that there's different levels of voting going on in a cortical column. There's multiple layers of cells in layers 2, 3, and I think they're doing slightly different things. So I just want to point it out that Vivian was talking about voting a second ago across modalities, which is not exactly the same as what's happening in this image. This isn't a single modality, and we need to know the features at relative positions to each other. I hope that wasn't confusing, but they're not exactly the same. But just
right.
on.
Yeah, no, that's a good point. So okay, well, how could self-attention be like voting? Well, assume that these weight matrices we normally learn are all the identity matrix / we just don't use them. So the key, query, and value beddings are going to be the same. They're just going to be the original vector kind of representation that was coming in. What this means then is the more closely those embeddings, so the X vectors, are already to each other, the more they're going to attend to each other. And so what that basically means is, the token here is going to attend to itself, and about equally it's going to attend to this token, and similarly vice versa. They're both going to ignore this token. And so what you'll kind of get as the output of this, the kind of value, is essentially just a kind of blending of these two similar ones, which maybe might correct for a bit of pose disagreement between them. And so that's kind of where the similarity starts coming in. But you might reasonably wonder, okay, well, maybe this only works when kind of they agree strongly with each other. What if there's kind of legitimate disagreement about objects? So we've kind of talked about this before, that if the pose is consistent mutually consistent for two different columns. Like let's say, you have a mug and a phone next to each other. This phone isn't going to be telling the column processing this mug, you should be seeing a phone, because with that relative displacement, then you would expect that you'd be on a different object. And so I'm not claiming transformers are doing this, because as mentioned, their kind of positional embeddings are a bit, are very fuzzy and kind of not at all explicit. But in theory, the actual self-attention mechanism has no issue with this, in that if these different columns disagree completely with each other, then you will, using this kind of format where the original embedding is the key query and the value, then you're only going to attend to yourself when you differ from everyone else.
So if the weight matrices, sorry.
Oh no, go ahead.
If they're just the identity matrix, how can the mug be recognized in the first place? Because I mean, the input will not be mug; it will be like a feature on the mug.
Yeah.
So how does it even get to that stage?
So there's a couple answers to that. So one is you could have this as a different attention head. So you would have an attention head that is the identity matrix, and that's doing voting like this. But you'd have other attention heads that are doing kind of more interesting things. And I'll kind of get to that later. The other thing is, you're absolutely right. Like, because we have no kind of reference frames that are updated over time through movement, all this kind of stuff, we're relying entirely on voting for kind of understanding anything, or rather relying entirely on lateral connections for understanding anything. So if you're only doing literally voting, then you're not going to get anywhere. But I think the most important question is, like, what if you have kind of a source of noise? So like, it's all well and good that if you already decide you're a mug, you just say you're a mug, and whatever. That's essentially happening in both these cases. So not that particularly interesting. What's interesting about voting is, what if a column is kind of unsure? Can the consensus that's emerged around it in other columns help it to become more certain? And so in this example, kind of assume this central token has sort of equal evidence for car and mug. And this is, again, represented by maybe two orthogonal, the kind of combination of two orthogonal vectors. Basically, when you kind of do this self-attention, it's going to attend to itself well, because it's itself. But it's also going to attend a reasonable amount to these other objects around it, because it has some evidence that it might be representing that. And what that means is, when you do the softmax, you're going to get some kind of non-zero values for all these other columns. And basically, when you kind of then produce the new value for this token, it's going to be a blending of these different columns, depending on how unsure or certain this column is about whether it's a mug, will depend on how much it ignores those things around it versus how much it decides to kind of integrate their evidence. So if it was like, 80-90% sure it's a mug, but a little uncertain, it's going to much more quickly take in that, or it's going to have a more significant kind of influence from the others. If it was only 10% sure it was a mug, it's probably going to mostly attend to itself and just ignore the other ones around it. And actually, as the number of other columns, like adjacent columns that it's self-attending with around it increases, the more of an effect those columns are going to have. Does that, make sense before I move on? Or does anyone take issue with? Okay, because then I just thought some fun random trivia. So that's, hopefully convince you that self-attention can, under these special circumstances, do something like voting. I then came across this interesting quote. The quote columns are like attention-weighted interactions between different word fragments in a multi-head transformer, but they are simpler because the query key and values are all identical. And the role of the intercolumn interactions is to identify these identical kind of embeddings. Any guesses on who said this?
ChatGPT, I don't know.
Jeff Hinton.
Yes, that's correct. Regarding the Glom architecture. Jeffrey Hinton. But I just think it's interesting because, yeah, when he came out with this Golem architecture, a lot of people drew parallels to Numenta's work, and which he doesn't mention at all in the paper, even though he talks a lot about kind of columns and basically describes voting. But he does compare his work to Transformers, and so I just thought, yeah, it was the same kind of point that the key, query, and value vectors are all identical to the embedding vector. But then there's definitely some caveats to this. So yeah, 100% the positional encodings are less explicit. They're kind of all entangled in this. There's no, yeah, real kind of clear notion of space in the same way as in Monty. This assumes kind of pose votings at the object level. I think this kind of gets to what you were saying earlier, Vivian, that like, yeah, like in Monty where, you know, we're voting, what you call it? Yeah, at the object level, you know, do we agree, mug, but, oh yeah, but sorry, but then the pose in Monty, we're kind of, where are we on the mug? Whereas what I've kind of represented here, we would be more saying like, where's the mug in space, like maybe in body-centered coordinates. And then, yeah, and there's kind of, yeah, again, no recurrence within each token. I feel like, yeah, this kind of has an interesting outcome in that if you imagine, like, let's say you are doing this and you're relying on this to kind of converge towards a certain representation and actually kind of use voting for this purpose. Let's say you're 50% sure, but, you know, like when you do the softmax, this might only get nudged like a little bit towards certainty. And let's say, you know, you want to iterate and kind of move closer or whatever. Basically, you'll need multiple layers of processing to do that. So you would need like a very deep transformer, I guess, to handle that situation. And yeah,
how deep are these networks in general, like these large language models?
Good question. I mean, I think what was the original one? It was like 6 or 8 encoder, and then something similar for decoder, or 12. But I have no idea how deep the latest ones are.
Birds
have 12 layers, for example.
This ones are like over 100. I'm not sure the number.
Well, all right, so that's very interesting question. 12 is really different than 100, because I remember like going back to the convolutional networks or image, they're big, they had hundreds of layers or something like that, 100 layers.
Well, so here 12 layers doesn't mean, it means 12 transformer blocks. Each block has multiple layers.
How many blocks?
And GPT has, I think, 96 transformer blocks.
Yeah,
Which GPT? GPT-3.
Yeah, GPT-3.
I don't know the form.
Okay.
So that without this recurrence, and there's no feedback, so are you always reliant on the entire stack to get your answer? I mean,
yeah,
you are.
But there's a lot of work of actually like doing fast inference by exiting early, that you don't need to go through like 96 layers of transformation to get your answer.
Yeah.
So there's a lot of work doing that, but they train it, you gotta train the whole thing, and then you could maybe do faster inference. A few layers.
That's interesting. Yeah.
It's you know, either that's not to be dizziness. It's just to say these are fundamental differences. You know, without the recurrence, without the feedback, you have this feed-forward system. It's quite different. And maybe that's nothing new to saying that, and just reminding ourselves of that.
Yeah.
How does it, you know, we spend a lot of time thinking about like compositional objects, objects made of other objects, and reusing models inside of other models. Is there anything equivalent to that here?
Yeah, it's a good question. That was kind of one of the main things I didn't get around to kind of a satisfying answer. So I don't touch on that here, but I could get back to you on that. I mean, there's I will talk about kind of yeah, on the next object, kind of like how you recognize an object composed of parts, but that doesn't necessarily address the situation of kind of like sort of arbitrary, like fast binding between things. I mean, self-attention, I guess, can kind of do that. in the sense that like, yeah, let's say, this is the word is blue, and then this is, I don't know, Volkswagen or something, and so that's like a novel combination that was never encountered in the training set. Maybe it's such that these kind of key query values have been learned such that Volkswagen knows to look for adjectives, blue knows to look for nouns, and so we can come up with a kind of vector embedding that combines those two. But that's a very kind of like mushy kind of just like add everything together way of representing things rather
It's not
than like
compositional either, right? It's not.
I mean, I don't think there's an explicit mechanism for compositionality. It's more like if for some parts of the data it would be more efficient at compositional representations, it might learn it for some aspects. It's just, but it's not like it's generically doing compositionality.
But if I learned a model of something, let's say I was doing a vision network, and I learned a model of something, okay, and now that appears as part of a larger image of not a larger object, it's not a separate thing anymore, it's not part of a larger object. Will I say, oh yes, this larger thing has the model I learned earlier, or does it say, no, I got a new larger thing and I'm just going to learn the statistics of its parts? Does it, let's say for example, I knew what a bicycle pedal crank looked like, and I know that it's, and I've learned what pedals look like, and now I see it in different machines. It might be a stationary bike, and it might be a human powered wine press. I don't know. Would I say, oh, that's would it know that yes, I recognize there's a pedal and there's affordances, or is it going to say here's a wine press and this is just some statistical part of it?
I think it can do it can do some of it.
Some, yeah.
It's not.
I think that's why
all these answers are going to be fuzzy like that, because I think in a lot of cases, because it's trained on so much data, it will just realize it's more efficient to think about pedals and cranks and apply it to different things, and it'll do it. But if it's only seen very few pedals, it's not going to do that.
Like if I saw a machine I didn't recognize before, it was a wine press and it was human powered with bicycle pedals attached to it. I might be able to figure out what's going on and say, oh, well, there's some human's going to be using this thing to provide power, and then where does the chain go? Okay, it goes over here. It looks like it's going to turn this tub or something like that. I mean, that's the kind of thinking that I would go through, because it's built of components that I've seen before, and I might figure out how they work together.
Is there a way we could test that with just language? Because then we could just input it to ChatGPT.
I don't know.
So, I mean, I think Jan LeCun
fragments and put them together and see.
Jan LeCun recently had this thought experiment, which was like putting a bunch of cogs that are rotating either clockwise or anti-clockwise in like series, and then asking like, okay, one cog is turning, what is the direction of turning of, the nth cog or whatever.
A cog for you is a gear? Is that the British term? For
yeah,
gear?
sorry, like a gear. and maybe, yeah, French, English, no. Yeah, and there was kind of a bunch of tweets about kind of whether it could, like sometimes it kind of solved it, but only if you told it Jan LeCun was wondering whether it could solve it, and stuff like that. But yeah, I mean, I think definitely.
It can do general computation, right? It's not Turing complete. So there's problems that require polynomial time to solve or linear time to solve, and it's not going to be able to do those things, right? You can't. If like sorting requires n log n time, and you give it a list of 1 million numbers, it's not going to be able to solve it. Right.
But yeah, I guess this problem was like designed
to up to a
to
point, but it can't. It's not a general computing.
Yeah.
thing.
Well, then again, I don't like using computing because we think of it like digital computers, but I do think it computing in the sense that
The more abstract notion of computation.
But
Theoretical.
right. Like maybe okay.
And some problems just are known to require polynomial time to come at an answer. And it probably won't be like traveling salesman problem.
Right, but no one can
Won't be able to
solve
do
that. Nothing can solve the shopping salesman problem.
Well, of course you can. Computers can solve it. Just
Well,
takes
not perfectly.
time.
Well, a big enough problem, we don't have enough time in the universe.
Right.
So,
But up to a certain point, it can solve it. Whereas I think transformers won't be able to do arbitrary Turing computation.
You know, it's funny because we use the word attention. I think it's completely different. Well, it's not completely different, but it's certainly, again, it's one of those words that it sounds the same and maybe it's similar, but it's really quite different. If I see something I don't understand, it's a composition of components that I haven't seen before. I narrow down my attention till I see various things I do understand. And then I say, okay, what are the relationships to those things, and see, can I see parallels to other things I've seen? So it's not this feed-forward process. It's an interactive process where I have to literally attend to different parts of an image or different parts of something that's happening in my life. And here they have the word attention, and but it seems like a very feed-forward. There's no recurrence to this. I can't walk through hypothesis serially or something like that.
Well, with the chat, with the autoregressive stuff, it's continuing to feed things back in. But that's feeding back. It's just running this. It's running the same algorithm, but it's taking its output and putting it back. Yeah, it's active. It's what we call active prediction, right? And so it can diverge very easily. Right, so it's taking a prediction, sticking it back in, treating it as ground truth, going and predicting the next thing, treating it as ground
That's
truth.
interesting. It's not exactly what I was talking about, but it's part of it.
Yeah, that's the thread that Niels and I had on Slack. It's that's one of Jan LeCun's main. That's why he says these are fundamentally limited, because it's just essentially only doing active prediction. It's not grounded in any way once you once it starts going.
Yeah. Right. That leads to its hallucination.
That's what leads to hallucination.
Right, because there's no additional information.
No.
You and I would look at something we don't understand, and we would try to, attend to different parts and try different hypotheses thoroughly. But
each time we get more sensory input.
Right.
Yeah.
We get more sensory input, and we don't just confabulate our way through the results. I don't say, well, I think it's a dog. Well, if it's a dog, then it's going to bark, and if I think it's barking, then it's going to say this, and whatever,
It's just once you give it the query, it's just, the input, it's just going to hallucinate from that point on.
Right. I mean, it's interesting. I'm really trying to get a sense for the fundamental component differences here, and it does feel like this idea that we're moving, sampling the world. Not randomly, but we're moving and sampling the world constantly. And sampling the world is not just moving our senses, but it's attending to different parts of the world. And we're building these models dynamically in real time.
You see, that part I think it's sort of doing in brute force. Like if we're given an image, we attend to different parts of it. When it's given an image, it attends to every possible combination.
Right.
And so it is in the superset of attending to each one.
That's been the history of technology in some ways, that we can build machines that are better than humans in a lot of capabilities, right? And in some sense, one could argue, like I always use the word, we have calculators, they're superhuman, right? They're really great. And then sometimes you can argue that, computer vision should be better than human, right? Because you can do this, you can do what you just described, right? You can look at it all at once, you can train like a billion things, but humans can't do that. So it shouldn't be surprised that things, even like these chatbots, are really, really good at faking it in some sense. The question is, are they really have any? Is it more than faking it? Is there really true knowledge about the world inside and that can be taken advantage of? So far, I don't think so, but I'm not certain that. I don't know. I'm asking questions, trying to get a better sense.
This is the whole it's just very brute force,
right?
And you can do really well as long as you have
right. And we of course we as humans look at language, which is language is already a very sort of it's an abstract way of communicating an internal model state that I have to you, and so it's abstract from the beginning. It's already post understanding. It's like we're coming up with description, words or tokens represent my internal representations that I'm going to communicate to you, which could be completely fake. But here we're starting with that, and that's all you get. You don't have any of the ground truth of knowledge about how the world actually feels and looks and sounds. You just have what the words correspond to. But anyway, we're really good at assigning, like, oh, a human will say, oh, this language is really good. There must be a human on the other side of it. There must be something really smart on the other side of it. In the same way, we might look at the output of a calculator and say there's a really great mathematician on the other side of it. And you get used to it and you say, oh no, it's this. It's just doing its thing, and I doesn't really understand what. Anyway, I'm just rambling. What else do you have?
Yeah, so I guess a few different things. Just one last thing to say on this kind of question of compositional objects. I just thought it was worth kind of highlighting, like, yeah, I think where these things excel seemingly is, yeah, they are good at this kind of fuzzy combination of these vectors, which might represent different things, and that's why I guess it's impressive that, you know, something like DALL-E or Stable Diffusion, you can say, you know, I want a hedgehog made out of lettuce. And it seems to be able to take kind of fuzzy concept of lettuce, the fuzzy concept of hedgehog, and kind of create something that seems like a reasonable interpolation of these two things. But on the whole kind of compositional thing, it's, you know, it's relying on this self-attention, which doesn't have a very explicit sense of space. And that maybe is why they, on the other hand, struggle with like something as simple as like, I want a blue cube next to a red sphere, you know, with a yellow pyramid on top of the blue cube. Like it will get the colors associated with each object wrong kind of as often as it gets them right.
Is that right?
Because, yeah, I mean, at least DALL-E. I don't know DALL-E 2. I don't know about Midjourney 5 and stuff like that. But that was definitely an interesting example of like DALL-E 2 could do all these amazing things, and it can't do 3 colored like geometric objects.
Wow.
So yeah, so it does really well as if there's like one thing.
This is like related to the compositionality theory. It's like,
Yeah,
a hedgehog made of lettuce is one thing, but these
Yeah.
3 objects with 3 different colors and 3 different positions, it's 3 things.
yeah, and it needs to kind of keep track of where they are in space and you know what's associated with what, and that's where self-attention seems to struggle. And I mean, if Midjourney 5 has solved that, I imagine it's just through brute force rather than anything, because they are kind of famously have better hands now, although they're still not perfect. But and that was another thing we talked about recently, which I think is kind of a similar problem. Like it's one thing to have like a fuzzy representation of a hand, but to have a very clear sense of like, okay, I'm going to do 5 fingers, you kind of need a more explicit representation of space.
Yeah.
But yeah, I do have a few things. Yeah, let's see if we can get through the rest of it.
Let's get to the conclusion here.
Okay, yeah, reference frames. Yeah, so do transformers work with reference frames? Well, you know, they use positional encodings at input, which is a small step maybe towards something like reference frames. And yeah,
it's what we did in the temporal pooler, right? I mean, it's the same thing. We said, okay, let's solve this simpler problem of one-dimensional reference frames. And then before moving on to the more difficult problem of, you know, not n-dimensional, 3-dimensional reference frames. So it is a significantly simpler problem.
Right. Yeah, and you know, so there's some evidence they have better kind of spatial awareness, which I'll get into, and yeah, there are some, you know, with a kind of neuroscience psychology background who have compared kind of their computations a bit to grid cells, the fact that they have these kind of spatial encodings.
I was just going to say, I don't think it's key to their success. New models don't have position encoding, right? They use alibi. They just replace it for like a learned bias instead.
What does that mean? You get rid of positional encodings of words?
Yeah, I mean, you have a learned position encoding instead. You don't have like the version that Niels was showing.
Yeah, but it's still a learned positional encoding.
Yeah, it's still position encoding, but it's just not like.
How does it learn? Aren't I feeding in text one word at a time, or no? How's it? Or you're saying no? It's not like that.
Well, you have like a bias that indicates where that would be in the sequence, but that you're not like giving it beforehand. You're just initializing and letting it learn through backpropagation. So it's not exactly a position encoding. I don't see alibi as a position encoding at least.
Okay.
I don't know if you.
Well, I mean, it's a mapping from, like, let's say it's a sequence. I mean, isn't it like, let's say again, it's the 4th token in the sequence. A learned encoding would just be like, a mapping from 4 onto a certain vector, and you just learn the weight transformation that does that vector.
Right.
So like that vector presumably is still capturing information about 4thness. It's just yeah.
But the
So
data
yeah, so I'm not suggesting it's specifically cosine or whatever. Just the fact that there is positional information that is maybe
but
key
when these systems are trained, They're not,
Yeah.
they are trained with, I mean, the only information you have are the tokens and their positions relative to each other. There's nothing else, right? There's nothing to be learning on. There's no other additional information about the world. It's just these tokens and where they are relative to each other in a one-dimensional reference frame. I'm stating that to see if I'm wrong about it, but that seems like sort of fundamental truth here. That's all you've got for your training data.
Yeah.
So there's no more position. There can't be any other positional information other than, well, this thing was in this position relative to this one. No. Well,
Yeah.
with language, it's a sequence. I guess I don't know what happens when you do this on images.
Yeah, and you could do a variety of things, as mentioned. Yeah, often they just do a raster kind of where they just flatten the image essentially into a bunch of kind of concatenated rows. But there is also work where they kind of do a more like 2D kind of what you call it, relative displacement in X and Y and things like that.
But even that's not what you really want about the world, right? Because what's relative, what's next to each other on your retina may have absolutely nothing to do with what's next to each other in the world.
Yeah, so yeah, I could kind of get into this here that yeah, you kind of have all these different flavors, and it can be absolute, it can be relative, and yeah. But just to say kind of, yeah, reference frames. So there's some evidence, for example, that transformers, visual transformers have more of a shape bias than, for example, CNN. So, you know, are getting kind of closer to humans maybe. But it is interesting to note, if you look at this graph, you know, the difference between VGG or ResNet 50 in general is much smaller than the difference between these visual transformers and humans. Sorry, I should explain this figure. So this is, here we have different shapes, and the more you go to the left, so at presentation time, you take these different shapes and you put a random texture on it. So you might have like an airplane, but with like the texture of an elephant skin. And you basically ask the system or the human to classify it. And humans will classify based on the shape most of the time, which is what you're seeing here. But other systems, particularly like old CNNs, will tend to focus on the texture and just completely ignore the global shape.
This gets back to our morphology models versus, you know.
Yeah, exactly. So it seems like, yeah, okay, maybe adding these positional encodings is doing something for transformers, but it doesn't seem to be enough, maybe because it's not explicit enough.
Well, are transformers on that chart too, or those?
Yeah, they're the pyramids, these yellow and orange ones. So you can see they're the best of all the different networks. The other ones are CNNs. Yeah,
okay. Well, that's a pretty telling chart, I guess.
Yeah, I suppose maybe one caveat to add to that, there's been a few different papers around this kind of question, and some of them suggest that it's also just the fact that transformers tend to be trained on a lot more data. So it's not totally clear whether it's really something special about transformers, but yeah, but I think this one controlled for that. Okay, so yeah, this kind of yeah, then gets into, okay, how can we do kind of, yeah, recognizing, let's say a mug based on this kind of self-attention operation. And again, this is going to assume a simpler form of self-attention than like a, you know, a special case rather than like the full one that's possible. So basically assume that a set of the set of the key, query, and vector weights are the same, which is to say that when we're doing a particular attention head, within that attention head, oh, actually, yeah, I think that's right. Yeah, within that attention head, we're going to see basically the same key value and query. And then, yeah, basically we have these input representations. Let's say they're kind of rim and handle with associated kind of positional embeddings. And if you have these kind of different but reused weight operations, you could imagine them learning to kind of transform, for example, from rim at, you know, a particular location to mug at a particular location. And this kind of gets very much to what we've kind of explored in the past, which is this more kind of capsule network type operation where everything is kind of just directly learning to predict, given a feature at a location, what is the relative position of the object to it. But once that's done, once you have those operations, then again, or like the outputs, then again, you could just kind of compare these, and they would kind of attend to one another if they had good agreement. So yeah, so then about kind of positional encoding embeddings, yeah, just to say basically there's a whole bunch of different varieties that you can do. As Lucas said, they can be learned or they can be hard-coded, as the one I described at the start was. They can be added, they can be concatenated, they can be in relative coordinates, absolute. They can even be recurrent, which seems a bit odd given the mass parallelization that transformers do, but yeah, you can essentially have the position encoding at the kind of nth position be recurrently dependent on the position encoding at the n-1 position. But a kind of key thing is they're typically at the input only. And so, yeah, one thing I was trying to research, but it didn't get around to was like how much, and so I'd be curious if anyone knows, like how much work is there out there kind of, yeah, using concatenated representations and kind of making sure that there's a separate representation at each layer, because it seems like there's a risk otherwise that the kind of spatial representations get sort of washed out as you get deeper and deeper, unless there's a really good objective function that's ensuring that they're, absolutely important, and that maybe this contributes to the kind of, yeah, there.
I don't think rotary invariants are input only. Like, I didn't get implemented, so I didn't read the paper fully. But I know for sure it's not an input only because you got to change every attention layer. So there is something going on at every layer level.
Wait, which one is that, sorry?
Rotary. That's the one they were using before Alibi.
Oh, is that the one that's used in Palm-E?
I think, yeah.
Where they like rotate the matrix?
I'm not.
I mean,
I know it's
okay.
not at every layer, but I didn't really get to read the paper. But take a look at that.
Okay, cool. Thanks. Yeah, there was definitely one that I saw from Google where they would like rotate the embedding instead of like adding to it, which was kind of interesting. But okay, cool. And then, but yeah, just to kind of point out, yeah, versus Monty, at the input, we're at least at the moment and likely to use kind of absolute body-centric coordinates that are in kind of 6 degrees of freedom, but then the kind of real computing is happening at these object level internal representations. All of this is very explicit. And I guess we also have kind of stronger skip connections for positional information. So although the skip connections might help the preservation of some of this for transformers, I think that's, yeah, again, because we're keeping the spatial pose and everything like that very explicit and separate, I think it's more likely that will kind of make it deep into the architecture in Monty. So yeah, this is kind of the limitations I already just talked about. I think just the one last one to mention is, yeah, that these transformations, all these weights and stuff need to be learned for transformers to be able to do any of these kinds of operations, whereas Monty learns very quickly based on sensory motor movement and then uses those graphs to just directly determine, okay, what is the position I expect to be, or the pose. Okay, so this will hopefully be an interesting one. Sorry if I'm going a bit quicker. I just want to make sure there's time for everything, and then you can always, I guess we'll come back. But yeah, so embodiment. So this is, yeah, now starting to become a thing with transformers. And so just two kind of prominent examples. One is Gato. So this was from DeepMind, and this one was kind of interesting. I mean, as Subati's was kind of saying, these systems can be kind of autoregressive if they're of the generative variety, and they took that into an embodied setting where basically, you might have some fixed prompt, and then you kind of it receives some sensory input. Let's say like the output of a game screen that outputs an action, and all of this is represented. So it kind of, for example, received the game input tokens, then it output as the next token it kind of predicted was its action, and then it did another action, and then it gets, receives then the next sensory input, and so forth. And so this can, yeah, it can,
Is that done, I'm sorry, is that done serially, or is that?
That is done, yeah, that will be done serially at inference time.
Yeah.
I mean, it might get a batch of these at once. I don't know with the visual input, but what's kind of interesting is then, yeah, it does sort of have a sense of recurrence, and that obviously it can kind of just keep concatenating these. But of course, there's a limit to how long you can sort of continue this before you completely forget about your past. And it's also just very computationally intense because, yeah, you're essentially just doing all of these operations at every next step. So yeah, in order to kind of deal with this, they used an architecture that's kind of designed to have a longer distant horizon. But I guess the important thing is there's no recurrence really within the network. It's sort of recurrence with the input that it's dealing with. And that's quite similar for this more recent work, PaLM-E. So PaLM was this huge language model from Google, and PaLM-E was their subsequent work to try and leverage this for robotics with a multimodal model. And actually, yeah, this was presented recently at DLCT. And yeah, so they just explore, for example, can you get a robot to pick up these a bag of chips like this based on kind of a natural language prompt and an image. So it's multimodal in that sense. And then the model's job is to output more natural language, which will condition the robot's kind of action sequences that it can take. So for example, like grabbing something. But again, the way that they're dealing with embodiment
I
is.
want to be clear. They take
yeah.
the original prompt, then they create
Yeah.
a series of language steps.
Yeah.
They actually go through that. They actually generate these language sentences, and then those are mapped to movements.
Yeah. Yeah, and the model, as part of like the whole like end-to-end learning, the model has to, like the language model, whatever, has to learn like what are the reasonable outputs that will kind of actually map onto actions that the robot can take.
Interesting.
They don't do anything to kind of directly constrain that.
Right. They're going back.
But yeah,
they're going back through language to do that again. It's interesting. I mean, I don't have to say to myself, open the drawer and reach for the green bag out of the other thing. It's interesting, but
yeah, but then once it generates the language instruction, does it then go off and do the entire sequence, or does it keep like it does?
Yeah,
a little
so
bit?
This is the thing. So it at any given time point, it has access to the instruction. So that's the start of the sequence. It has all of the actions it's taken itself, like all the actions it's generated in natural language. And then it has the current visual input.
But what happens? What if you can't open the drawer, or I don't know. I guess something that requires a change in plan or something, right?
Yeah, so they kind of show that with the human knocks the rice chips back into the drawer. And so I guess at that time point, at the next time point, so it already said take the rice chips out of the door, but then the rice chips are back. And then it's but it sees the image. So yeah, so they're still there. So it basically just outputs the same action. So it's not like it I don't know, it doesn't understand why it's gone back or anything like that.
Okay.
And
I mean, a classic example might be I try to open the drawer and maybe there's a latch and I didn't know there was a latch, a button I have to press, right? So it says open the door, it doesn't work.
I mean, it's possible that it would have learned that, okay, I tried this and I see the image, and okay, on the next one it might attend more to the lock or something. I mean, I don't think it's inconceivable that it could learn to do that, but I think, yeah, it feels like the main kind of weird thing about this is like there's just a bit of a missing I mean, like world model and kind of just continuous representation, for example, of visual space. Like it literally just has the actions it's taken and its current visual input, which is of course very different from how we would kind of interact with and again, they're just like kind of concatenating all of this on top of each other and then just doing the full transformer operation across all of it.
again, it's not clear to me that, they might be able to get this kind of system working really, really well under certain environments, it's not, I don't know. It's hard to say how good they can get. This is just the beginning. Or maybe they'll run into fundamental issues. I don't know.
Yeah. But yeah, so basically, yeah, go ahead.
Do they then generate like sub policies to actually translate these sentences into motor commands or like joint movements?
No, I don't think so. But this kind of thing itself is sort of, I can't remember if there's also a step where it first chains together these things. Like it was either this or another paper where like, bring me the rice chips from the drawer, and then it's meant to first create like a bullet points of all the actions it's going to take, and then it says like, okay, first action, do this. So yeah, no, but I don't think they do anything with sub kind of policies, but yeah, no, it's a good question.
Just from my experience, it seems like it's so much easier to
a big jump
7 steps than to actually like take the rice chips out of the drawer. That seems like a lot more difficult than just writing out 7 steps.
Yeah.
Right. And what if the robot arm was in a different position than it usually was, or things were rotated. Would it? It's not. These could be very simple robotic commands if everything's fixed.
Yeah, I think the problem. Well, yeah, I don't know. If they considered that, or maybe it's something they're doing now, but yeah, I think in general they were trying to like really lean heavily on the language model, but I guess with the caveat that it's maybe not very good at describing these lower level things. But yeah. So yeah, I'll just skip over that. Yeah, so I mean, just the other kind of really big difference to mention is, obviously you have kind of either rapid sensory motor reference frame building, few shot based on real world inputs, or you kind of backprop on the like a significant chunk of the internet and absorb all the kind of horrible things that are out there. So that's just another big difference. So the last thing I just was hoping to talk about is kind of how can we maybe bring some of these ideas together. 2 caveats to just mention. I'm sure some of these things have been tried in the literature, but maybe not in combination, maybe not particularly in the context of embodiment. But yeah, that would definitely be a next step if we do want to think about this. Firstly, just check, and maybe someone here already knows. But I think kind of turning these token representations into something a bit more like an RNN, within that token. It's still part of a transformer, but just it also kind of updates itself based on its past history. And in particular, if there was maybe some sort of separation out of kind of pose embeddings from feature embeddings throughout the architecture, then I think this would get a bit closer to something more like Monty, and would make more sense for something like embodiment, where kind of rather than having to kind of constantly concatenate the full input at every like the full past and the full future when you are doing embodied learning, because this is what I meant by this approach is a little like they just keep adding like this one, it's like they keep adding kind of new columns onto the brain or recruiting new columns if you imagine that these are columns. Whereas if we assume we have a fixed number of columns we can deal with, you can still process like the visual input and whatnot in parallel, but you keep track of history through this kind of more self-recurrence within a given column, and that would be more similar to what kind of Monty would do. And then making this kind of voting this kind of special case, so it might already be happening, but it kind of requires that the attention heads learn the identity operation. I didn't get time to check whether that's like an observation that ever happens. That would be interesting if it does, but maybe adding some additional attention heads to the ones that typically are there could just mean that that's like an extra computation that the system has access to. The kind of the feed forward layer could ignore it if it feels relevant. And this maybe kind of would be a bit like skip connections, how they kind of do the identity operation, just like passing information through the system. It would also be parameter free, because there's no weights involved, or these kinds of other weights I was talking about for the kind of more transformer type, or sorry, capsule like object processing. Because again, the key query and value in this case is shared for a particular attention head, then I guess that would be like 1/3 the typical parameter count cost. So yeah, these could maybe be kind of interesting inductive biases to try. And yeah, so kind of some of these changes could be made to kind of pre-trained networks and then kind of further fine-tuned, but obviously there's a lot of detail that would need to be done to kind of think through whether it would actually work or what problems there are. But some of the kind of more complex things to introduce would be, these kinds of things like top-down connections. I think, that would maybe cause issues for backpropagation. Just kind of explicit spatial models, how to do that. I don't know if the kind of recurrence and that sort of thing would help kind of have that emerge naturally. It would be a bit similar to then, like the representations would be a bit similar to some in the literature where they found like grid cells kind of emerged just through learning. And then kind of what you were talking about, Jeff, like this whole kind of compositional object, sort of like rapid binding between reference frames and features. It's not clear that there's any kind of easy solution, again, without kind of explicit spatial models.